So, hello professor, my name is Davidson Tandanu with student ID 108990015 from ICS department, and today I'm going to give you some information about optimizers used in deep learning. So, these are the main body of my presentation today, includes introduction, main content, and conclusion. And this is the introduction to optimizers used in deep learning. So, as we all know that algorithms for deep learning involve optimization. And the praise of optimization itself refers to reducing objective function or increasing objective function, or often known as a cost function or loss function. There are attempts to figure out the optimal parameters that effectively reduce the cost function given the deep learning dataset. And to get the ideal parameters for deep neural networks, this is where gradient descent is implemented. So the accuracy of a deep neural network model is impacted by the optimizer's functionality. And although deep learning falls within the category of parametric techniques, it aims to loosen up as many assumptions as possible. Gradient descent is the method for extracting parameters from the data, and the optimizer choice for neural network and many machine learning techniques is gradient descent, or GD. Applying adaptive learning optimizers to address some of the problem with the traditional stochastic gradient descent, or SGD, and SGD with momentum. SGD with momentum that varies in deep and deep learning model training is iterative and requires the specification of an initial point to begin. This initialization has a significant impact on the majority of algorithms, and the traditional SGD and SGD with momentum have demonstrated their appropriateness for deep neural network learning, and it is also inevitable for approaches to be improved. With this is why a set of adaptive learning techniques was created. However, as time goes by, there are many new optimizers that been developed by engineers in order to make a better optimizers. The invention of adaptive learning algorithms such as like RMS prop, AdaGrad, and Adam, which compute the learning rate for each parameter, was a step for creating a better optimizer. And deep neural networks frequently use the Adam optimizers by default, according to recent research. And in this report, I want to study and compare the different types of optimizers in deep learning that can help neural networks models fast reach, find, or approach their corresponding optimums, and also comparing the performance of each optimizers to the traditional gradient descent. And so the main content of my optimizers used in deep learning. So how do optimizer are algorithms or techniques that modify the neural network properties such as its weight and learning rate in order to minimize losses, and by reducing the function, optimizers can solve optimization issues. So so to make an analogy, you can visualize a hiker trying to descend a mountain while wearing a blindfold as a help, as a and then even while it's impossible to predict which way to move, there is one thing you can determine: whether he is moving upward or downward. For upward, you're losing progress, or downward, you're making progress. And then you will eventually reach the base if she keeps moving in a downhill direction. Similar to this, Uh, it's hard to know your model weight at the beginning, but you can possibly get there. But though, with a little bit of trial and error based on the loss function, uh, that is if the hiker is descending, and the optimizers utilize determine how you should modify the weights of learning rates of your neural network or minimize losses. The goal of optimization itself is to minimize the losses and deliver the most precise outcomes. Uh, Various optimizers are researched within. There are some various optimizers that are researched within the last few couples of years, and each having its advantages and disadvantages. And these are some of the optimizers. First one is the traditional gradient descent, and the second one is stochastic gradient descent. Third one is mini batch stochastic gradient descent, and the fourth one is SGD with momentum. Fifth one is adaptive gradient of R at grad, and then there's the delta, RMS prop, and last one is ADAM. So move on to, so before we go through gradient descent and the variation, we have to know to a local minima where it is our aim. So gradient descent is the local minima is to our aim to get the bottom of the graph where cost versus weight here, or to a point where we can no longer move downhill or local minimum. And the gradient itself is to measure how much the output of function change if you change the inputs a little bit. And for the learning rate, to reach a local minimum, you have to set a learning rate to an appropriate value. And we cannot set learning rate to be too high or too low, because because if the step is too big, it may not reach the local minimum, and also it will bounce back and forth between the convex function or the gradient descent. And if we set the learning rate to a very small value, the gradient descent will eventually reach the local minimum, but that may take a while. So that's why the learning rate should never be too high or too low for this reason. Now we go through the gradient descent. The gradient descent is the iterative techniques that aims to modify a collection of parameters until it finds the best set of parameters that result in the smallest loss function value. And it moves in the direction opposite to the steepest ascent to iteratively reduce the loss function. And in order to find the minima, gradient descent is reliant to the derivative of the loss function. And how gradient descent works is it uses all of the training sets data to determine the cost function gradient to the parameters. And for the advantages and the disadvantages of the gradient descent, for the advantages is easy to compute, easy to implement, and easy to understand. But some of the disadvantages may trap at local minima. Weights are changed after calculating the gradient on the whole dataset. So if the dataset is too large, then this may take years, or will take too much time to converge to the minima. And it also requires large memory to calculate the gradient on the whole dataset. So now the second one is stochastic gradient descent. The stochastic gradient is instead of taking the whole dataset for its iteration like what gradient descent do, we randomly select a batch of data. So that means that we only take a few samples from the dataset. And when we compare to gradient descent approach, the path taken by the algorithm is full of noise. since we do not use the entire dataset, but we do further batches of it for each iteration. As a result, SGD requires more iteration to reach the local minima, and the total calculation time grows as the number of iterations arise. But however, the calculation cost is still lower than the gradient descent optimizers, even after doubling the number of iterations. And the result is that this SGD should be chosen over batch GD algorithm if the data is large and the processing time is crucial to consideration. And the advantages and disadvantages for SGD is the frequent updates of model parameter, and it requires less memory, and it allows the use of large datasets as they has to update only one example at a time. But the drawbacks is the time required for completing one epoch is large compared to GD algorithm, and it takes a long time to converge and may stuck at local minima. For the mini batch SGD, we only use a subset of a dataset in this version of GD to calculate the loss function rather than the entire set of training data. And fewer iterations are required because we are using a chunk of data than the entire dataset. So, because of this, the mini batch GD algorithm runs more quickly than the GD and the SGD. In comparison to earlier iteration of GD, this approach is more reliable and efficient because the technique leverages batching, so all of the training data does not need to be placed into memory, making the information process more effective. And additionally, the mini batch gradient descent algorithm cost function is smoother than that of the SGD algorithm, but it is noisier than that on the batch gradient descent technique. And mini batch gradient descent is therefore the best option and offers a fair mix between speed and accuracy. And some of the advantages and disadvantages of mini batch SGD is that it leads to more stable convergence, and it has more efficient gradient calculations, and it requires less amount of memory. But the drawbacks are mini batch gradient descent does not guarantee good convergence, and if the learning rate is too small, the convergence rates will be slow, and if it's too large, the loss function will oscillate or even deviate at the minimum value. The fourth one, we have SGD with momentum. Due to the fact that the SGD follows a more noisier path than the GD technique, so it takes more iteration to obtain the ideal minimum, which resulting in a highly slow calculation process. So because of that, we use stochastic GD combined with momentum technique to solve the issue. The momentum helps in accelerating the loss function convergence, and SGD modifies the weights in accordance with gradient oscillation in either direction, and the process will go a little faster if a fraction of the prior update is added to the current update. So when implementing this technique, it's important to keep in mind that a high momentum should be used to reduce the learning rate. It is SGD with momentum denotes the gradients and converts faster as compared to SGD. And to speed up the process even more, you might consider using high momentum and learning rate. But also keep in mind that as momentum grows, the chance of passing so that it also there's a chance also of passing the ideal minimum, and pure accuracy and even more oscillations might follow from this adaptive or adaptive gradient. It in comparison to previous gradient descent methods, the undergrad differs slightly. This is due to the fact it is various learning rates for every iteration. The difference in the parameters during training determine the change in learning rate, and the learning rate changes less noticeably the more the parameters are altered. So, in real-world datasets include both dense and sparse features, and therefore this change is very advantageous, uh, and therefore also having the same learning rates for all traits is unfair. And the advantages of undergrad is it eliminates the need to manually adjust the learning rate. But the drawbacks is its aggressive and monotonic learning rate reduction sometimes could make the learning rate drop dramatically, which compromise the model's accuracy. The Now the fifth one is ada delta. So with a lot of iterations, the learning rate of the prior method undergrad gets quite low, which will cause slow convergence. That whereas ada delta algorithm has the concept to take exponentially fading average in order to prevent this. So ada delta is a more powerful of the undergrad that adjusts the learning rate based on a moving window of gradient updates rather than adding up all the previous gradients. And ada delta gains new knowledge in this method even after numerous revisions. And in contrast to undergrad, ada delta's original version does not require to define an initial learning rate. And the advantages of the ada delta is we do not need to set a default learning rate, but the disadvantages is computationally expensive. Comes the RMS prop or root mean square prop. The algorithm's primary objective is to shorten the number of function evaluation necessary to obtain local minima, so that it will quicken the optimization process. The algorithm divides the gradient by the square root of the mean square and keeps a moving average of the square gradients for each weight. So, to put in another way, it works by penalize the updating of a parameter. So if it costs the cost function to oscillate the load. Imagine if you create a model to categorize various fish species, and the model mostly uses the attribute color to distinguish between the fishes, but it thus commits numerous faults. That's where RMS prop penalizes the parameter color in order to let it to rely on other attributes as well. This will keep the algorithm from adjusting to change in the parameter color more fast than it will to change in other parameters. When compared to earlier iterations of gradient descent algorithms, this technique has a lot of advantages in comparison to GD algorithms and its derivatives. The approach compares quickly requires less adjustment, but the drawback is the learning rates must be manually defined so that the suggested value is not suitable for all applications. Now, as we go to ADAM, or adaptive moment execution. It is so in order to update network which during training, this optimization algorithm is a further extension of SGD. ADAM Optimizer modifies the learning rate for each network separately, unlike SGD training, which maintain a single learning rate. And the designers of the ADAM optimization algorithms are aware of the advantages of the ADGRAD and RMS-prop algorithms, which are two other stochastic gradient descent extensions. So as a result, both the ADGRAD and the RMS-prop algorithms features are integrated by the ADAM optimizers. ADAM uses both the first and second moments of the gradient to adjust the learning rates rather than just the first moment, as it does in RMS-prop. And since ADAM optimizer is commonly used because of many advantages, some of the advantages is it is less tuning, it runs faster, and it uses less memory and has a lower memory requirement. But there is also the drawbacks, where it frequently focuses on faster computing time rather than data points. So because of this, algorithms like SGD generalize the data more effectively, but at the expense of slow computation. So when we compare GD, the traditional GD, the SGD and MBSGD, for GD, it runs through all the samples in your training dataset and to do single update in a particular iteration. But for SGD, it is only one of training sample to do the update for parameter in the iteration. And for mini batch SGD, it is a subset of training a sample from your training set to do update for parameter in an iteration. So we know that in terms of accuracy, GD is more accurate compared to SGD and mini batch SGD, but in terms of the speed of time conversion, mini batch SGD is more quicker than SGD and GD. So comparisons of optimization algorithms in deep learning. So there's a researcher tries to compare a researcher tries to do an experiment on testing on each of the optimizations algorithms available for now, and the test consists of MNIST that includes 60,000 training and 10,000 test example, each of which is a 28 by 28 grayscale handwritten digit image. Cipher 10, which is composed of 50,000 training and 10,000 test example, and Kaggle flowers, which contains 4,242 images and five different types of flower. And last one is LFW, or label face in the wild, which includes 13,230 face images belonging to 5,700 people. And the researcher then used supervised and unsupervised learning tasks, where the supervised learning task is for the classification and the unsupervised one is used for reconstruction. For classification, the researcher used convolutional neural network, and for the reconstruction She used the convolutional autoencoders, as you can see from the table below. This is some of the results for the classification and supervised learning tasks. As we can see from here, uh, uh, if there's sometimes there's other delta with the biggest accuracy percentage, and for in the MNIST, and for the cipher 10 there's Adam, the one I explained in my report, and the biggest accuracy percentage is Adam here. And then for the LFW we have Adam and RMS prop, and then for the Kegel flowers we have Adam also. This is for the classification, and for the reconstruction, the loss percentage, as we've seen from here, Adam has the least loss percentage of the test on all the datasets like MNIST, Cybertan, LFW, and Kegel flowers. So these are some conclusions of my report. Is that SGD is fairly a simple technique that is currently rarely used in applications because of how slowly it computes, and the algorithms itself, consistent learning rates for its epoch is another issue. And since Adam optimizer has many advantages, Adam is suggested as the default optimizer for the majority of applications as a result of all of that. And the Adam optimizer may offer the best chance of obtaining the finest outcomes for your application. And it is also crucial to understand the needs kind of data where we are working with in order to select the finest optimization technique and provide amazing outcomes. This is my presentation video, and that's it. Thank you.